Hello friends, welcome back to my channel, and in this video we will solve a problem where we evaluate the energy of a modulated signal using Parseval's relation. The problem statement goes like this. So we have a message signal with a bandwidth of band B hertz and it has energy of EM. So now the question is we have to evaluate the energy of the modulated signal y of t given by m of t cos 2 pi f naught. And what is f naught? F naught is a modulating frequency and that is given to be 10 times the bandwidth of the message signal. So let us see what is given. So we are given that the message signal m of t is a bandwidth, message signal m of t has a bandwidth of b hertz and energy of E. Now if you let's use Parseval's relation. So what does it say? The energy of any message signal m of t is given by Em would be equal to the integral minus infinity to infinity m square of t dt, and in frequency domain that would be equal to integral minus infinity to infinity m square of f df. So indirectly it means, so the energy is nothing but the area of the signal m square of t in time domain, and that is equal to area of the signal m square of f in the frequency domain. So one important thing that you should note is the shifting a signal either in time domain or frequency domain doesn't affect the signal. So for example, I have let's say I have a signal m of t minus 2 or t plus 2. So that signal also will have the same energy of em. Same is the case in frequency domain. So I have the frequency, the Fourier transform like m of f plus, let's say 10, or m of f minus 20 or something like that, that also will have the same energy of em. So this is a very important concept, and we will use this in coming slides. Okay, so now again let us go back to the question. So we have to find the energy of the modulated signal given by y of t is m of t times cos 2 pi f naught, and we are given the modulating frequency geared to be 10 times the bandwidth of the message signal, which is reasonably larger than the bandwidth of the message signal. So now we are asked to evaluate the energy of the modulated signal y of t, and again by taking the help of Parseval's relation we see that Ey, which is energy of the signal y of t, would be equal to what? According to the definition, that should be the area of the signal y square of t, which is nothing but integral minus infinity to infinity y square of t dt, and again in frequency domain that would be the area of the Fourier transform of y of t, which is square of the Fourier transform of the y of t, which is y square of f df. Okay, so in time domain it is the area of y square of t, and in frequency domain that is area of y square of f, and these two are equal by that result we get by using what is called Parseval's relation. Okay, so now by taking the Fourier transform of y of t, which is m of t cos 2 pi f naught t, what do we get? So this is by using what is called modulating property, we get y of f to be equal to 1 by 2 times m of f plus f naught plus m of f minus f naught, but we were given f naught to be is equal to 10b, so that is what I have substituted here. So if you remember the previous slide, so we have to take the square of y of f and then we have to integrate that square to get the energy of y of t. So first let us square y of f, which is nothing but y square of f is equal to, so note that this is looking like just like a plus b whole square, so that's why you will get 1 by 4 times m square of f plus 10b plus m square of f minus 10b plus 2 times m of f plus 10b times m of f minus 10b. So that is what we have got, m square of f plus 10b plus m square of f minus 10b plus 2 times m of f plus 10b times m of f minus 10b. So what is that you observe is that, so the let's focus on the third term, which is the product of m of f plus 10b, m of f minus 10b. So what is that you observe? M of f plus 10b, this guy is centered at 10b, and we know that m of f has a bandwidth of b hertz, and hence m of f plus 10b that will have a support of 2b hertz from minus 11b to minus 9b. Same is the case for m of f minus 10b. So this fellow is centered at plus 10B, and that fellow has a support of again 2B hertz, which is varying from 9B to 11B. And this first term is centered at minus 10B from minus 11B to minus 9B. Second term is centered at plus 10B from 9B to 11B. So definitely what is that you observe? So there is no overlap of these two terms, and hence what can we say? We say that that product would be equal to 0, and hence our y square of f will get simplified to this. Only first two terms exist in this y square of f, and that is given by 1 by 4 times m square of f plus 10b plus m square of f minus 10b. Okay, now let us go back to the energy of the evaluation of energy of the modulated signal. So this is what we have got, right? Now we just evaluated y square of f term. So let us substitute that. So we got y square of f to be 1 by 4 times n square of f plus 10b plus m square of f minus 10b. Now if you integrate, we get this. So now let us split the integral. So you get 1 by 4 times integral minus infinity to infinity m square of f plus 10b df plus 1 by 4 times integral minus infinity to infinity m square of f minus 10b df. Okay, so yes, let us evaluate that. So we have got this result, right? The same thing I have replicated here. So what is that we have discussed in the beginning of the video? We discussed that the energy of a signal is not affected by the shift either in time domain or in frequency domain. So we will use the same result here. So what did we have? We have the shift of m of f in frequency domain to the left by 10b units. That should not affect the energy of the signal, and same is the case here. Here you see that there is a shift of plus 10b for m of f, and that also should not affect the energy, and hence what happens, the first term, the integral in the first term is equal to em, and integral in the second term also would be equal to em, because energy is invariant to shift either in time domain or in frequency domain. So what do we get? We get ey to be equal to how much? 1 by 4 times that integral, which is equal to em, which would be m by 4, and 1 by 4 times this integral, which is again equal to em, and hence we get em by 4. So what would be ey? Ey would be em by 4 plus em by 4, which is equal to em by 2. So this is just the half the energy of the actual message signal m of t. Yes, so what is that we have seen in this video? We have seen that energy of a modulated signal is half the energy of the message signal, provided the positive and negative shifting of the spectra are wide enough that they do not overlap with each other. In a typical communication setup, this is usually the case. So with that, we conclude the topic of finding the energy of a modulated signal, and I hope that you have enjoyed this video and learned a useful concept. Thank you.